Hello, and welcome to the next video in my series on basic statistics. Now just a reminder, this video is geared towards individuals who are relatively new to stats, so maybe a student in an introductory stats course, or someone who just needs to brush up on basic stats concepts. Now in this video, we're going to continue our discussion on measures of variability, and more specifically, this video will deal with the concept of z-scores. This is something that's actually relatively simple, but many students get confused about it in introductory stats classes, so we'll go over the very specific, basic ways in which we use it and how it's calculated. Now I'm going to use the same problem I did in the previous video, and in that example we had two classes, 5 students each, which would be nice, and they took an exam, and these are their exam scores. So the first class had an 85, 95, 75, 80, and 90. Their mean or average score was 85. Class 2 had 88, 79, 91, 85, and 82, and their mean score was also 85. Now they have the same mean or average, but does that tell the whole story? Well, as you can see in this line graph, Class 1 and Class 2 both have a mean of 85. But if we graph the actual scores along an axis, we can see that Class 1 scores have a much wider distribution. They're much more spread out from the mean. Class 2, the scores are closer into the mean where the green stars are. So even though both classes have the same mean, their variance, or their standard deviation, or the distribution, or the spread, use whatever term you like, is wider for Class 1 than Class 2. While both have the same mean, Class 1 has greater variability, so the scores are more spread out in Class 1. So let's talk about z-scores and the relationship to the standard deviation. How far is any given data point from the mean? And when I say how far, I actually mean distance. I want you to think about the z-score as a measure of distance. How many standard deviations away, above or below, from the mean is any given data point? So, how far away from the mean is a data point? And that could be above the mean or below the mean. If we're looking at a line graph, so above the mean would be to the right, and below the mean would obviously be to the left. I want you to think of the standard deviation as a ruler of sorts. The standard deviation becomes a measuring unit. And common ones are feet, yards, miles, light years, minutes, kilograms, and even things that are standard like paper clips. So I could get standard paper clips here next to me, and I could actually measure out the length of a piece of letter paper. I can measure it out in paper clips because the paper clips in the box are all the same size. I could do the same thing. I could measure the little wall next to me in how many iPhones I could, line up across the wall. I could measure the wall in iPhones because at least any current generation of iPhone is the same. So it's a standard unit. So all of these are standardized measures. And that means that a foot here in the United States would be the same thing as a foot in another country. Even if they use the metric system, a foot is still a foot. Okay, same thing for minutes. So a minute on my clock or watch is the same as a minute in France. It's a standardized measure. And a standard deviation is the same thing. It's a standardized measure. So z-scores are standardized measures where the unit is a standard deviation. So I can say that, this chair is 3 feet from me. I could also say a data point is 3 standard deviations from the mean of my data. Same idea. It's just a measuring unit. Now the z-score, since it measures just distance from the mean, it ignores the actual measurement units. So if our data is in feet, our z-score would not have feet as a unit. It would just be a z-score of 1.5 or -2 or whatever else. Now, since a z-score is a measure of distance from the mean, we set the mean of our data to 0 because the mean is 0 distance from itself. So that's why the mean has a z-score of 0. And then we measure the distance from the mean by the number of standard deviations away any given data point is. So here's a really simple example. Let's say we have some data and our mean is 50 and we have a standard deviation of 5. So a value of 55 would have a z-score of +1 or +1. The value of 55 is 5 above the mean, and our standard deviation is 5. So the unit of standard deviation is 5. Our data point 55 is 5 above the mean, so our z-score is +1. Now a score of 40 would have a z value or z-score of -2 because it is 10 or 2 times 5, 2 deviations below the mean. So that should be pretty straightforward, and you could see how the z-score is actually derived using the standard deviation and the mean. Now the formula for z-score is just any given data point minus the mean divided by the standard deviation. So you can see the z formula in a couple different ways. It just depends on the book you're working with or something like that, but the basic idea is the same. So in the left-hand formula we have z equals x. Now x is our individual data points in our actual data, minus the mean, that's x bar of our data. So we take that difference and we divide it by our standard deviation. Now sometimes that's denoted as s, sometimes it's denoted using the Greek letter sigma. It just depends on which book you're using. It does the same thing. So over on the right we have z, and that's x minus mu divided by sigma. It's the same thing, okay? So data point minus the mean divided by the standard deviation. So let's actually just compute a few z-scores so you can see exactly how it's done. And once you see this example, it works for any other example you might do. So this is the score distribution or the score list for our class number 1. So remember we had 85, 95, 75, 80, and 90. Now the standard deviation for that data is 7.9. So we have everything we need. We have scores and we have a standard deviation that we could find on a calculator or in Excel or a stats program or even by hand, because standard deviation, if you look at my previous video on standard deviation, we calculate it by hand. So there are scores, standard deviation, and then the z-score formula there at the bottom. So now we actually have our means. So we have a score column and a mean column, standard deviation, and our formula. If you look at the formula, the first thing we need to do on the numerator, on the top of the fraction down there, is take each score minus the mean. So in the first row, we have 85 minus 85. Well, that's 0. Then we have 95 minus 85. That's 10, of course. And then on down the list. So in the top of the z-score formula, score minus mean, we just do that for each pair of data there. That's it. Now the next thing we have to do is divide that difference by the standard deviation. So if you look in the top right for the first row of scores, you can see that I went ahead and put the entire formula in there, each part of it, so you can see where it's coming from. So z equals 85 minus 85, and of course that's our score minus our mean, and that's 0 divided by 7.9. Of course 0 divided by anything is always 0. So that has a z-score of 0. It is 0 away from the mean because, well, it's on the mean. Now the next one we have 95 minus 85, which is of course 10, divided by 7.9. And that gives us a z-score of positive 1.27. Now that should make sense, because our standard deviation is 7.9, our difference is 10. So we know it's going to be a little bit over 1, because 10 is a little bit over 7.9. So when we do the division, we have a z-score of 1.27. Of course, the next row we have 75 minus 85. Now that's negative 10 divided by 7.9, and that is a z-score of negative 1.27. Okay, this is very simple. So if you go down to the next row, 80 minus 85 is negative 5. Negative 5 divided by 7.9 is negative 0.63. And then there in the blue, those are actual z-scores. Okay, so we would say our second data point has a z-score of 1.27. Our fourth data point has a z-score of negative 0.63. And that's it. It's just that simple. Let's look at this sort of in a visual way. Now I'll set this up so we have our mean, which is x bar there in the middle. Of course, that's the number 85 in our data. And that, of course, has a z-score of 0. Down below, I have our standard deviation of 7.9. So now I've added in to the right of x bar. Now we have x bar plus 1 standard deviation. Now, I want you to think about what's going to be there in the red, where the red question mark is, and what will be where the green question mark is. Well, we added 1 standard deviation to our mean. So our z-score is 1, or positive 1. Now at the top there in the green, remember, since we added a standard deviation to our mean, that number will be 85 plus 7.9, which is 92.9. Now let's go over to the left. Now we have x bar, our mean, minus 2 standard deviations. Now what will be in the red and the green? So now our z-score is negative 2, because we are 2 standard deviations below the mean. So a z-score of negative 2. Now above that there in the green, or we have 85 minus 2 times our standard deviation. So 85 minus 2 times 7.90. And of course that is 69.2. Now, based on those two examples, you should be able to fill in the rest of this chart. And there it is. We can see that in the middle we have our mean, x bar. Then we have x bar plus 1 standard deviation, x bar our mean plus 2 standard deviations, and then x bar plus 3 standard deviations, and then there on the left we have the minuses. Now our z-scores are plus 1, plus 2, plus 3, because remember, it's just a measurement away. So what we're saying there is the first one is 1 standard deviation from the mean, the next one, a z-score of 2, is 2 deviations from the mean above it, and then so on and so forth. And then the opposite there for the left-hand side in the negatives. And then to figure out our numbers above, it's just simple mathematics. If we're 3 deviations above the mean, then we just have x bar, our mean of 85, plus 3 times our standard deviation of 7.9. And that gives us 108.7. And then we do the same thing there for the negative side. Now what I've gone ahead and done is actually added in our data points from our class where we actually found the z-scores. So everything in this line chart at the bottom, the line graph at the bottom is the same. So we have all of our numbers there. And what I've done is actually made the tick marks on the line. Those are actually standard deviations. So you can see that we have a z-score of 0, 1, 2, and 3, and then negative 1, negative 2, negative 3. And then above that, there in the black, those numbers correspond to our green numbers in the chart above. Now our test scores, we actually have to place them within our line graph here. So in the middle, we actually have our test score that was 85. Remember, that was a z-score of 0 because it's the same as the mean. Then our test score of 90 was 0.63 standard deviations above the mean. So it has a z-score of 0.63. Now look at the score of 75. That is a z-score of negative 1.27 because 75 is 1.27 standard deviations below the mean. So here's where you actually put your data points into your distribution where you found your z-scores and such. So it's just basically subtraction and division. That's all it is. So just remember, we took 80 minus 85, which was negative 5, divided by our standard deviation, which was 7.9, and we get a z-score of negative 0.63. And that should make sense. If our standard deviation is 7.9, then a score that's 5 away from the mean is going to be a little bit over, halfway to the next standard deviation, because 5 is about 63% of the distance to 7.9. So same thing as above. I just went ahead and actually put our data points on there so you can see it visually. Now in another video, I actually did some analysis of NFL field goals. Of course, those are field goals in the National Football League here in the United States. And I looked at where the ball actually started for the longest kicks in each season. So I collected the data for regular season field goals by each kicker that had at least 10 field goal attempts during the 2010 and the 2011 seasons. And I generated a graphical tool for visualizing our data using the football field diagram. And then I computed the field goal ball placement and the line of scrimmage, like where the ball is actually snapped from, for the field goal length. Then I computed the mean, standard deviation, and coefficient of variation for the line of scrimmage for each year. And in case you didn't see my previous video, the coefficient of variation is very simple. It's just the standard deviation divided by the mean times 100 to get a percentage. Okay, so basically it's what proportion of the mean is the standard deviation. So standard deviation divided by the mean. And again, this was like a coach saying, okay, we moved the ball down to X yard line during the last play. Should we try a field goal to win the game? So here's what I found out for the 2011 season. Now you can see this looks very similar to our test data earlier in the video. So for the 2011 season, the mean line of scrimmage, and that's where the ball is actually snapped back to the kicker from, was the 36-yard line. Okay? Now as you can see, the standard deviation was 3.6 yards. So if you remember in our test data, our standard deviation was 7.9, I believe. In this case, it's 3.6 yards on a football field. Now, I measured that off, as you can see it there in the blue tick marks, away from the mean. So the plus 1 SD is plus 1 standard deviation. That's about 3.6 yards away, or to the right of, the mean. And then plus 2 is 3.6 further than that, plus 3 is 3.6 further than that. And the same thing for the left-hand side. Okay, so this is the exact same thing we did in the previous test data. As you can see, all the beginning line of scrimmages fall within a z-score of -3 and a z-score of +3. Okay, and that's not by accident. That's actually something we're going to be talking about over the course of the next several videos. Now here's 2010. Now here the mean was 35.5 and the standard deviation was 4.2 yards. So in this case, the 2010 line of scrimmages for the longest field goal kicks was a little bit wider. It had a wider distribution. The standard deviation was a little bit longer. And you can actually visually see that. You can tell that the tick marks in the 2010 season, which represent 1, 2, 3 standard deviations away, it's actually a further distance. But again, all of the kicks are within -3 standard deviations or +3 standard deviations, which is the same thing as saying all the kicks are between a z-score of -3 and +3. Okay, so let's go ahead and just review real quick and we'll be done with our talk about z-scores. Just remember, it's about how far is each data point from the mean. It's distance from the mean. So how many standard deviations away, above or below, from the mean is a data point? It turns the standard deviation kind of into a ruler. So if you remember on our graphs, we had little tick marks. 1 standard deviation away, 2 standard deviations away, and so forth. That's all a z-score is. So something that's 1 deviation above the mean will have a z-score of 1. It's a measuring unit. Now z-scores themselves ignore measurement units because it's just distance from the mean in the number of standard deviations. The mean is always a z-score of 0 because any, a data point that is the mean is 0 distance from itself. And we measure the distance from the mean by the number of standard deviations away it is. And again, here is our example. A mean of 50, a standard deviation of 5. So the value of 55 would have a z-score of +1 because it's 5 above our mean. Our standard deviation is 5, so that's a z-score of 1. If you think of it in your head, what's the calculation going to be? It's going to be 55 minus 50, which is 5, divided by our standard deviation, which is 5. So that's 5 divided by 5, which is +1. Now for a score of 40, again, that would be sort of the same process. That would be 40 minus 50, that's -10. -10 divided by our standard deviation of 5 is -2. So a z-score would be -2. All right, that wraps up our discussion on z-scores. They're actually very, very simple to calculate, but they are very important in later statistics because z-scores come into play when we're comparing two different samples or two different populations or something like that. So they're very useful, very handy, and you'll be seeing a lot of them in the future. Again, thank you very much for watching, and I look forward to seeing you again next time.